Hey everyone, PFA in the editing bay here. Apparently you can hear the sound of my computer fan going in all of my audio for this episode. Oops, I didn't think you'd be able to pick it up, but it has. My computer is in hospice care. I'm moving things over to a new one. So the rest of Galileo will have this noise. Sorry. Just imagine it's another part of Galileo that's broken.
And welcome back to End of Mission. We finally made it to Jupiter.
I'm Paul, the pressure-fed astronaut.
And I'm Face of Sarcasm. I'm the beautiful voice you heard at the beginning. And we're back.
Yep.
We're at Jupiter.
I am 6 days old.
Yes.
It's December 7th, 1995.
A date which will live in... Wait, no, that's the wrong...
That's a different... Well, it is... And okay, I'll just tell you, this picture was taken on the third orbit of Jupiter, so this is... I'm sorry. But...
Wow. How dare you use artistic creativity to illustrate a point and have a dramatic shot.
Yeah. Wait, I gotta click on this now. There we go. Alright. Okay. So now that Galileo is orbiting Jupiter, it's gonna do some science, right? That's why you're here.
To count some dust.
Yeah! The most important thing imaginable is dust counting.
Oh, yeah, it's on every single mission.
Every one of them. So the primary mission is exactly 2 years long. December 7th, 95 to December 7th, 97. That's the primary mission. This is, okay, we're at Jupiter, let's do everything. We'll design the spacecraft to last this long. We know it's going to do this, right? That's what primary missions are, right?
Right.
Because like the Mars helicopter, right, Ingenuity, was supposed to fly 5 times. Mm-hmm. It's flown, I think, 75 times, and I think it tipped over or something. They lost communications with it just yesterday. So, yeah, a whole bunch of things just died this week in space.
Dang. R.I.P.
So you can see, Galileo slimes on in, right? So you can see that's the orbital insertion, and it's going to spend 6 months climbing up here.
Oh, jeez.
Yeah.
We made it to Jupiter, and we're leaving.
Well, you gotta remember, you gotta measure the atmosphere, the magnetosphere of Jupiter, right? It's kind of big.
Right.
It gives you a chance to do all that. Also, it's about mission design too.
Yeah.
Right. Minimize amount of propellant you need to use.
Right.
So during this long cruise to apogee, that's when they transmit all the atmospheric probe data to Earth. Again, right? Yeah. So you can see that's kind of what they're planning on doing. So. Right. And they'll do this for the rest of the mission, right? You can see the different orbits. They'll just toss the information once they do the flyby.
Right.
Now,
so they get the information when they're close by, and then they toss it out when they're far away.
Yeah. So the encounter, I actually have a diagram of encounters for later parts of the mission. They'd start, like recording here and here, and they do the flyby there, right? All the because that's we'll get into that. So in March 1996, the apogee motor fires again. Mm-hmm. To raise the orbit out of the intense radiation field of Jupiter to higher up. So it does the primary mission. So you can see, even in the primary mission, it doesn't do any IO flybys. The only IO flyby was coming in.
Right.
Which they didn't do, which is unfortunate.
They didn't collect any data for it because they were saving it for atmospheric probe. So
what's interesting about this mission trajectory design is it used gravity assists the whole time.
Ooh.
And it was so what they did was they do a flyby, and the flyby would toss an orbit that would fly by another moon on the next orbit.
So the previous flyby would set up the next flyby.
Yeah, so you could keep, right, so you minimizes your trajectory correction maneuvers, makes it a lot easy for propellant management, really cool for trajectories, and it's an interesting byproduct of, I think it's the ratio of Jupiter to the size of its moons and their, like, resonances.
Oh, yeah, because, they're in orbital resonance of 124, right?
Yeah, it's 124 and then Callisto.
Yeah.
The only other planet that does this is Uranus, with it and its moons. So there's actually been proposals to do a Galileo-style mission to Uranus, which I support that fully, because that's an interesting system. So that's kind of what's going on.
And plus I want to probe... yeah, never mind.
You're not doing that.
Yeah.
No.
Okay.
Bad.
Stop it.
Stop. So... they'll do 11 orbits of Jupiter, and the orbits are named for the encounter that's going to happen. So the first flyby is going to be G1 Ganymede on June 27th, 1996.
Okay.
It's going to fly by Ganymede at 835 kilometers, or about 520 miles. So
that's close.
It's really close. So the next orbit's going to be Ganymede in September at 261 kilometers or 162 miles. Like we're getting really close, right? Then it's going to do Callisto in November 96, kind of far away. Europa in December 96, and then the fifth orbit, they actually aren't going to do any observations because Jupiter's Earth's going to be blocked by the sun.
Oh, so they can't transmit any data.
Yeah, they don't want to risk it. Because, I mean, something else will break, you know? The dust counter will explode or something, right? Then we do another flyby of Europa in February 97, Ganymede in April and May, Callisto June and September, and then Europa in November 97. And this will make kind of the end of the primary mission for Galileo.
Okay.
And you can see it gets pretty close in some of these, you know, 300 miles, 200 miles.
162 miles, yeah.
It's just really, you're doing flybys. These flybys, of course, toss it to the next moon, and you get some really good imagery. Because they also want to shape the flybys, so it's not just the same spot they'll fly in front of. They'll do over the poles, they'll do the equator, they'll go to the side, you know, they'll sneak up on it.
See different parts of the moons, yeah.
Yeah, because, again, you're here, take pictures, learn what you can about it.
Yeah.
So for the next part, I'm not going to do this chronologically because that's kind of annoying. I'm instead going to talk about each moon on the way as it goes out, and then Jupiter and everything else. So extras.
Ooh.
So we're talking about right now. This episode's just going to be the primary mission of Galileo.
Right. We're finding the monolith.
Yep, that's what we're doing.
Yeah.
Jupiter and beyond the infinite.
Exactly.
Okay. So this is Io, and all the pictures I'm using are for when they were for the primary mission. So this was taken in 1996.
Okay.
And so this is Io. So Io looks like pizza.
Yeah, just slathered up in a mess of different colors.
Yeah. There's volcanoes. Its radius is about 1,820 kilometers, so about 1,200 miles. It's a bit bigger than the moon.
Oh, okay.
Surface gravity is a bit higher than the moon. It's 0.18 Gs.
Okay.
So, you know, it's decent. And it orbits Jupiter every 2 days. It's just cooking, right? It's swirling around. And all these moons
cook this pizza.
Yeah, this pizza's cooking all right. And it's tide locked. So the same side faces Jupiter, because Jupiter's really big and really close.
Yeah.
Earth's moon is tide locked. Earth ain't that big.
It's 300 times less massive.
Yeah, so this thing orbits Jupiter at about 421,000 kilometers, 262,000 miles, which is about the moon's orbit.
Oh, okay.
So it's like the moon in a lot of ways, except everything else. Except everything else. Yeah. So Io's, I think, is one of the most distinctive moons of the Jovian system. It's pocked by volcanic features. The yellow, red, orange surface is from sulfur compounds released during volcanism.
Oh, okay.
Yeah.
So it's just sulfur.
This is just sulfur compounds, and the different colors of sulfur are from different temperatures of heating.
Okay.
Yeah, right. So the blacker spots, that's volcanoes.
Okay.
And you can see different like volcanic rings from eruptions. Actually, we'll get a close-up picture of this one, I think, later on.
Oh.
Yeah.
Okay.
Its surface is changing. Galileo would record changing surface features throughout the mission.
Well, yeah, it's volcanoes. It's just volcano. There aren't any craters on the thing.
No, because they get surfaced over by a volcano.
Yeah.
So the first observations, because Galileo did take pictures, so they do the flyby of a moon, and during that period also look at the other moons, if it got a chance to. So that's how we got all these pictures of it, right? So they determined that there were over 100 active volcanoes on Io. Which,
jeez.
Yeah. So, for example, one of the biggest rapid changes was there's a 250-mile diameter dark spot formed by volcanism over the course of 5 months. So they looked at it once, and then 5 months later, this big dark spot just formed.
Jeez.
And what they observed is that the lava, the magma of Io, is about 2,700 degrees Fahrenheit.
Oh, wow.
So don't touch it.
Yeah, that's hot.
They also observed volcanic plumes up to 120 kilometers high. It's like 75 miles high. Which, you know, again, if that was Earth, New Shepard does not go this high.
Oh.
Yes.
Jeez. So it's just chucking it.
Yeah. We got to remember, it's got 18% gravity. You can do that.
Yeah, but still, it's chucking it.
Oh, there's bigger ones. Later, we'll see bigger plumes.
Jeez.
So when they did these flybys of the moons, what they also observed, because you're doing a flyby, right? You're doing a change in velocity. You're actually feeling a tug of gravity on it, so you can actually kind of figure out how much it weighs, roughly.
Oh, right, because mass is.
And you can kind
gravity,
of guess the mass distribution of the internal structure based off other readings.
Ooh. Okay.
So what they determined was that Io has an iron sulfide core that's about 900 kilometers in radius, about 560 miles.
Okay, so that's pretty hefty core.
It's a decent core, and it's sifted, right? It's shaped, so it's got a crust, a mantle core.
Okay.
So Io also possesses an ionosphere, which fluctuates in size and intensity with the volcanic activity. Obviously, it's tossing high energy particles out of a volcano into Jupiter's magnetic field.
Yeah.
And it's got the most active volcano in the solar system. It's named Loki because it's Marvel fans. No, I'm not joking. It's not Marvel, but they're actually named for Hawaiian volcanoes, actually.
And one of them is named Loki?
I think so, yeah. Yeah.
Interesting.
So this is Io.
Oh, dang.
Taken during the mission. So this is what Io looks like, and you can just see all these surface features, right?
Yeah.
Again, that just ring of sulfur, the different shapes, the big black spot, and that is an eruption.
Oh, wow. It's blue.
Yeah, it's the sulfur. It's the sulfur. I think it's the temperature of sulfur, and that's how you know it's what's going on. I'm not a geochemist, just so we're clear.
Jeez.
But yeah, you can see like there's mountains, just enormous mountains.
Oh, wow.
Yeah.
Look at that.
Yeah, it's a stunning world.
Yeah. Wow.
So then you can see here's another image.
Jeez.
There's an eruption. I think one of the images has another eruption in it. It's like somewhere around here, I think.
Dang, look at that.
Oh yeah.
Look at it. It's just covered in sulfur. It's just constantly spewing out stuff.
Oh, I just want to make a note here because I'm going to do this in the description, just so we're clear. So these are images from raw Galileo data, enhanced by a guy named Kevin Gill for JPL. Just want to make note of that.
So these are enhanced images. What makes them enhanced?
He just kind of pasted them together and kind of did some touch-ups on it. Because it comes in through 3 color channels, and he kind of made them to look the way they are.
Okay.
He stitched them. We'll see that when we look at other moons up close. He stitched some of the images together, just so we're clear. I just want to make note of that in case anyone's... it's NASA public domain for the most part, but I want to make sure we're all clear on that. But yeah, this is Io. Look at it.
Look at that thing.
It's just volcanism. Enormous patches of volcanic activity.
Yeah. Just nothing but lava flows.
Oh, look.
Or sulfur flows.
Look. There's a giant mountain there.
Look at the giant mountains. Yeah, right in the Terminator. You can really see them.
That's actually one of the things they did with flybys too, was make sure see if you can see the mountains, like the edges of them, so you can kind of guess how tall they are.
Yeah, but I mean, these look giant. You can clearly see them.
Oh yeah. It's amazing.
Yeah.
And they didn't even get up close with this during the primary mission.
Wow.
So again, there's another volcanic eruption. Again, it's Io. Oh, look, there's 2.
Yeah.
See, there's one there. There's one there.
Yeah.
It's just it's a stunning world.
I think the second one that you circled, I think in the first image on the left, that's the little
This one?
darks. No, the one below it.
That one?
No, go back.
Oh.
Too far. So so on the left image, lower than the circle.
This one.
I think that's the one erupting.
Actually, it might be. Yeah, because it could be making the plume right. Of course, I'm using yellow.
Yeah.
So that could be the plume or a giant spider.
Yeah, it's a giant spider.
It's a giant
spiders of Io.
Yeah, it's giant. Yeah, the giant spiders of Io.
That's constantly trying to kill with volcanism.
That just sounds like a 1950s, pulp story. The giant spiders of Io.
Yeah, it has about as much scientific understanding as the authors do.
Yeah. So Io is not. Don't do much on the primary mission because one flyby, December 7th, didn't do anything.
Yeah.
They're just looking at it.
Because of all the technical problems that
Galileo breaks a lot.
Yeah.
So now we're on to Europa. This is the one that everyone loves talking about. This is it's all the right. I made the little caption. All these worlds are yours. 2010.
Yeah.
So this one's I think the smallest of the Galilean moons.
Yes.
Yeah.
Yes, it is.
Because it's 1,560 kilometers so about 970 miles across. It's about 90% the size of the moon. Surface gravity is about 13% Earth gravity, and it whips around the moon, not the moon, the Jupiter. At every 3.5 days or so.
So twice as long as Io.
And it's about twice as far out as Io.
Yeah.
So, makes sense.
I mean, it's would be 1.5784 or something times the distance, because that's the resonance you get.
Yeah,
right?
because it's 124. Yeah.
Yeah, and that's because of the A cubed equals P squared.
Yeah, I remembered this when I was really interested in planets.
Yeah.
Wait.
I mean, they're fascinating.
Oh, yeah, they are absolutely fascinating, but rocket propulsion is more my speed. What kind of engine does Galileo have? What's its propellants? What's the pressurization system?
Ooh, it's pressure-fed engines. Ah, nice.
Yeah, correct. Yeah. Those didn't break.
Wow.
So Europa's that moon that everyone loves talking about because everyone thinks there's life there. Is there? Well, we don't know.
Oh.
So it's composed of silicate rock and with a water ice surface. It's frozen.
Okay.
It's a big frozen chunk of ice with rock in there.
Yeah, looks like a giant dirty glacier.
Yeah, and the surface, of course, is lined with they're called like line. I don't know how to pronounce any of this.
They're lines.
Yeah, lines which are cracks in the ice. But it doesn't have that many craters. It's actually one of the smoothest moons in the solar system.
Ooh.
Except for this crater right here.
Yeah, it's very noticeable.
It's Pywell crater. They actually thought it was a mountain because of how bright it was.
Oh.
It's not. It's a crater. It's the other way around.
It's a big hole in the ground.
Yeah. Now, of course, if you're a geologist, planetary geologist nerd, the lack of craters on Europa's surface means
it's young surface.
There's surface activity.
Yeah.
That makes it interesting. Now, magnetometer data suggests that there's a briny subsurface ocean in Europa. This is where they think life is. So the magnetometer data for the mission was different whenever they did a flyby of Europa compared to the standard Jupiter magnetic field, right?
Okay.
What could do that is briny, salty water because they're ions in the water, so you can measure that. You actually measure the changes in the magnetic field because of the ions, because they're going to interact with Jupiter's magnetic field.
Oh.
I am not a planetary geologist, mind you.
Okay.
But it's interesting.
Yeah.
There's a subsurface ocean. There's oceans. There's water.
So that's what's creating the magnetic differences.
Yeah.
Huh.
The ions interact with Jupiter's magnetic field, and that's what does it. So actually what they did was they observed Europa on one side of Jupiter, and then went to the other side to see if it would flip. Because if it was just Jupiter's magnetic field, it would be the same, right? It'd be aligned the same way. Mm-hmm. When they went around to the other side, it was opposite, which means there's an internal magnetic field generated by the ocean.
Oh, nice.
Yeah. And then the gravitational data from when Galileo did its flybys suggests that there's an ocean.
So there's an ocean under
all that
all
ice.
the ice.
Yeah.
There is an ocean.
Yes.
Wow.
Yeah. So there's also an atmosphere to Europa.
Really?
Yeah, it's tenuous, which means there's not much. The moon has an atmosphere, for reference. The Apollo missions made it about twice as big as it was.
Oh.
Not that big. So it's made of water and some other little particles. Tenuous.
Yeah.
But this is what Galileo saw.
Oh.
So these are ice flows, right?
Yeah.
And these are compared to San Francisco.
Oh, so these are big.
These are city-sized chunks of ice.
Jeez.
And just look at that.
Yeah, look at that.
It's just amazing.
Wow. And so it's basically just enormous amounts of icebergs just colliding with each other.
Yeah, they're moving around on top of this subsurface ocean.
So it's a giant frozen ocean.
Yeah. Well, it's not. The ocean isn't frozen. The surface is. The underside might be liquidish.
Right. So there's an ocean. There's a liquid ocean below with a solid frozen ocean on top.
Yeah.
Wow.
And it's just huge. Just city-sized icebergs drifting around on the surface, and they do move a little bit. I don't remember specific data on that. I don't remember that part, but and again, there's San Francisco.
Yeah, for comparison.
Yeah, and this is another big, like, high altitude shot of Europa, and you can see this flow of something, right? This shape, these cracks. We got the little ones here. It looks like cantaloupe, in a way.
Yeah, it's all just scratched up and cracked and broken, and
you got little they're called like sesame seeds. They're called little crater dimples that are kind of reddish. All around.
What are those?
I don't remember. Again, there's so much data from Galileo that just trying to parse all of it to something I could do in, our 3-part series is just, there's so much.
Dang.
And also I have another 2 moons to talk about.
Oh, yeah.
And Jupiter itself. So,
yeah.
So this is Pibble Crater here. It's a big crater feature.
Okay.
Again, the cracks, the lines, and this is, again, you see how big this is. This is a really big chunk of Europa that we're seeing.
Yeah, this is huge.
And this was one that was enhanced by Kevin Gill, as you can, he talks about this. This is where I got it. So there's actually JPL image database that I used, and then I used Kevin Gill's Flickr page, which, again, I've linked in the description. Don't worry. You can look at these. Okay. I didn't use all of them. There's so many pictures. But, and you can see, so what's interesting here, so take a look at these kind of ridges. What's interesting about them?
They're kind of doubled.
Yeah. Isn't that weird?
Yeah, that is. Why are they doubled?
I don't know. We don't know, really. I think the theory is that that's where kind of water ice is kind of going up, kind of like the mid-Atlantic ridge. Right? So it's kind of coming up like this as they're moving apart like that. Right? So more material just kind of comes up and deposits. I think that's the theory I read.
Okay.
Yeah.
Huh.
And they've got these lines, the ice, the water ice, just kind of frozen like that, and the different lines, and the crisscrossing, and got the big canyon system here.
Yeah, and a bunch of different depressions with red stuff in there that we don't know what it is.
Yeah.
Yeah, that is. Right. And it's all over a giant ocean
we've never seen the inside of.
Yeah,
we don't know anything about. We're only looking at the surface of these worlds.
Yeah.
We can only really kind of assess Io's interior because he keeps throwing it up.
Yeah.
But it's just... And these are just pictures. Just the surface.
Yeah.
It's astounding.
Yeah.
This is another picture it took. Again, these are enhanced images. We've seen what Europa really looks like from Juno, which it's a bit more gray, kind of more gray-brown.
Yeah.
Less, obviously, it doesn't, these enhanced images, but they look really good, though.
Oh, yeah.
It's an entire world. Okay, there's the
crisscrossing, and
the
double ridge,
the double ridges, which again, that is one of the big points of interest of Europa, is what's doing that, and the kind of what's going on there.
Yeah,
the geology, and these are stitched together, I think, by Kevin Gill, or this is from JPL.
Okay,
I can't remember. Again, it's both of those. I had both tabs open. I was like, okay, what pictures can I get? I typed in Galileo Europa. What can you find? Again, I've linked it in the description. You can go look for yourself. There's so many pictures.
Yeah.
And it's just gorgeous, too.
Yeah.
And, of course, this is the inspiration for ELU in Kerbal Space Program.
Yeah, obviously.
Yeah. It's an astounding place. Oh, this is it taken by NIMS. So hot spots, hot and cold spots. You can see you can see this feature right here, right? There it is on so good. There's stuff going on.
It's warmer.
Yeah. There is stuff going on internally in Europa. I wonder if, this might be the Jupiter-facing side. Tidal forces. Right? I think that might be it. Because if there's Jupiter there, Jupiter's like, come on. Give me.
Yeah.
Give me that water ice. I'm thirsty. I have a hot spot that an atmospheric probe went into.
Yeah. Give me your lunch money.
Yeah. Yeah, it's just, there's so many stunning images. And this. So this is about 1,500 kilometers across. I think this way is north.
Okay.
Yeah. Look at that.
That is... Wow. Oh, man.
It's an amazing moon.
Yeah.
All the crisscrossing, the different... You can see, right, this is different than this.
Yeah, that's... you can see the strands and the curves and...
The big river shapes too.
Yeah, the giant things. Wow.
You know, if I was a planetary geologist, I would have more to say with more to gush about.
Yeah.
We
All we have is images that we could look at and be awestruck by.
Which, again, look at this. This is Europa. This is a moon orbiting Jupiter.
Yeah.
Up close.
Yeah.
It's just gorgeous. Now we're going to Ganymede.
All right.
Ganymede is the biggest moon in the solar system. It is bigger than the planet Mercury.
Jeez.
Its radius is 2,600 kilometers, so about 1,700 miles. So 1.52 times the size of the moon.
So the moon is pretty. So the moon's pretty big.
The moon is pretty big. It is. It's a pretty big moon compared to the others. But Ganymede's even bigger.
Yeah.
So surface gravity is about 15% g. Again, about what you expect. Its orbit is about a little.
So wait, it's lower than Io's.
Yeah, because Ganymede's less dense.
Oh, okay.
Yeah. Because again, Io has a solid chunk of iron that's half its radius.
Yeah.
Right.
Yeah.
Ganymede's a bit bigger. So this orbits Jupiter a little over a week. So it's about 1 million kilometers, or about 670,000 miles out.
Okay.
Ganymede's the largest moon in the solar system. It'd be a planet. So like Europa, it's water ice, silicate ice surface composed of silicate rock, water ices. You can notice here, there's distinct light and dark regions on the surface. There's 40% light, 60% dark, or it's the other way around.
It's basically half and half.
Yeah, it's about half
dark
and half.
spots,
Yeah.
light spots.
So what they think is the dark spots are the older surface, and the light spots are newer. I think I should write this down.
Newer.
Yep. The light areas are called succulus, by the way. I thought that was interesting.
That's an interesting naming convention.
Yep. So the original surface, so the light is younger, dark is older. So the lighter parts, right? Because it's like water ice that's been kind of chopped up and flung around, whereas the darker stuff's been there baking since it formed. But the most exciting discovery that Galileo made about Ganymede is it's got a magnetic field.
Oh.
It has its own internal magnetic field, which is so it's got an internal structure, right? Crust, mantle, core, and there's an internal dynamo that's making a magnetic field.
Oh.
Kinda like on Earth.
Oh, okay. Oh.
Yeah.
Huh. So it's not an ocean underneath it, but rather.
Well, there's an ocean.
Oh, okay.
There's a subsurface ocean. Yeah. There's all these ice moons have oceans under them.
Wow.
Yeah. Huh. Even Voyager data from the Uranian moons, Titania, Miranda, they have oceans. Pluto might have an ocean.
Oh, oceans. Wow.
Well, you gotta see it this way. If the surface is water ice, the mantle would probably be water, like a liquid ocean like that, right? Technically, Earth's mantle is an ocean of rock, right?
Yeah.
Similar thing going on there.
I see. All right. I see what you mean.
Yeah. So this is Ganymede. Let's see what else. Also, they noticed the craters are flattened. Why is that? Why do you think that would happen?
Why would they be flattened? Would they be filled in?
Yeah, it's because there's surface changes going on.
Oh, okay.
So
I was wondering, like, how does the lighter stuff, like, what causes the lighter stuff, the younger stuff, to get chopped up?
Impacts.
That's it.
Yeah. Impacts. Probably some internal tides going on too, right? Does this look like an impact crater to you?
Yeah, that looks like an impact crater, but I mean, like, the general lighter sections of the moon.
Probably tidal forces, impacts, that sort of thing.
Okay.
Because again, it's still really strong with Jupiter's gravitational field, because it's
it's so big.
It's so big.
Yeah.
And you can see more surface features here, kind of like lines, right? You kind of see them.
Yeah.
Tidal forces going on there. And you got these weird river shaped, like they look like river deltas of just ice.
Yeah.
It's so cool.
Amazing.
So this is the surface.
Oh.
Of Ganymede. This is really up close.
That's lumpy.
Yeah, it's got impact craters, right? So this is Galileo kind of coming in edge on, taking pictures. You can see there's
Okay.
a bunch of right. It's got so you have the darker inside of the crater than the lighter outside, right? That's the theory. What's going on? So it's exposing the darker surface, which is the older part.
Oh, okay.
Yeah.
Huh.
This is again NIMS taking pictures of it. You can see there's stuff going on underneath the big dark spots there. See?
Oh, okay. It's not just being like warmed up more than
It's got to be
the lighter
I think
spots.
it's tidal forces that are doing. Yeah, it's Jupiter's tidal forces, and again, the internal structure is probably impacting it, right?
Right.
Earth's continents actually do experience tides too. Ours raise about 1 to 2 feet with the moon.
Oh, really?
Yes.
Oh.
Whereas
Wow.
the ocean will rise, like 10 feet because it's water versus rock.
Yeah. Rock doesn't like to move all that much.
Yeah. Except when it's liquid.
Then it loves moving.
Yeah. These are beautiful, stunning worlds.
Yeah.
It's kind of I should have got more pictures. There's so many pictures.
You're free to always. Viewers at home are always free to go check out these images themselves.
Oh, absolutely. So then this is again. So here's another surface feature, kind of like on Europa, right? You got all these craters, and you got this big like river of ice, right? They're
Yeah.
kind of colliding, and they're doing something. There's something going on there.
Yeah.
Don't know why.
It's just that's happening
Yeah.
for some reason.
We'll know in like 2030 when Juice gets there.
Oh yeah. Okay.
So, yeah, but
Look out for that coming up soon in 2030.
yeah. So yeah, but it's just like the best part of this was look at all the gorgeous pictures of these surfaces of these moons.
Yeah.
It's just so beautiful.
It's like look at that. You can see like a bunch of the cracks even in the other spots.
These guys, crags, yeah.
Yeah.
Oh, there was an image I wanted to include that I didn't get a chance to that showed a crater chain on Ganymede. So it was like a crater, and then another one, and then another one, and then another one, all in a chain, right? Because it's an object that broke apart and just hit it.
And just
Yeah, the moon's got
basically
those too.
carpet bombed. Yeah.
Yeah, moon's got them too.
Yeah.
You can find those. It's really cool. Shame I didn't put that in. I forgot to do that.
It's okay. I mean, there's so many
Oh,
pictures.
there's thousands of pictures.
Yeah. Wow.
Yeah. And again, just look at these lines.
Yeah,
The
look at
craters,
that.
They're just flowing around. And they got the darker bottom of a crater. And you got of course the top, it kind of forms back up into a mountain.
Yeah, a little mountain in the middle.
It's stunning.
Wow.
It's gorgeous.
Wow.
Oh, there's a crater chain. Right there.
Yeah. Look at that.
And you just see the rivers and the shapes and the channels and the canyons, and they're just enormous too. Gotta remember, these are geologic features viewed from 600 miles up, and they're that noticeable.
Yeah.
Right, from a camera built in 1983.
Yeah, this potato managed to capture these stunning photos.
And it was put onto a VCR basically and sent back.
Yeah.
It's amazing.
Yeah.
And so is Callisto.
Hey.
So
All right.
Callisto is kind of the other moon of the Galilean moons. Everyone talks about Ganymede, Europa, and Io because they're all, Europa's might have life, Io is volcanic, and Ganymede's huge. Callisto's kind of ignored.
Oh.
Unfortunately. So this guy is 2,400 kilometers, about 1,500 miles across. It's about 1.4 times the size of the moon, so it's enormous.
Is that still bigger than Mercury?
I think it's
Or
just
like the same size?
I think it's a bit smaller than Mercury.
Okay.
Yeah. Again,
So it's a moon the size of Mercury.
'cause I think it's Ganymede, Titan, Mercury.
Okay.
Yeah.
Yeah, it makes sense.
So this guy, about 13% G. It orbits Jupiter about 16 and a half days. So it takes its time.
Yeah.
It doesn't have the same resonance as the other inner moons.
Yeah, it's not on the 124.
Yeah, because it's just got to be the other guy.
Yeah, it's got to be different.
So it's the strangest of the Galilean moons. I'm going to say it. I mean, look at it, right? Of these, it's the most of the ice moons. It doesn't look like the rest of them, does it?
No, this one's definitely it's just covered in
It's more
white spots and impact craters.
It's more impact craters, right? I mean, Io, of course, stands out among them because it's not made of water ice; it's sulfur.
Yeah,
but
and also just covered in volcanoes.
Oh, yeah, it's a planet made of volcanoes.
Yeah.
So the most interesting thing I read when I was reading this was, so when Galileo did its flybys, right, it measured the internal structure. It doesn't really have one.
Callisto doesn't have an internal structure?
It does, but it's not like the other moons, right? So the other moons, right, Europa, crust of ice, liquid ice mantle, solid rocky core.
Okay.
Callisto doesn't have that distinctions. Doesn't have as big a distinctions.
So it's just kind of fuzzy?
Yeah, it's kind of fuzzy. I mean, there's still some differentiation, but not on the same scale as the inner moons.
Really?
It's just far out away from Jupiter that the tidal forces don't cause that to happen, apparently.
Oh.
It's so weird.
That is weird.
It also has a subsurface ocean because, all the cool kids have them.
Yeah.
So Galileo, when it did its flybys, observed evidence of a magnetic field, but we don't really know if it actually exists. It could just be the subsurface ocean.
Oh, okay.
Yeah. Again, could be from the briny ocean or the tenuous atmosphere, which is made of carbon dioxide. And then the surface, as you noted, it's more pocked with craters, right?
Mm-hmm.
It's most likely very old, so it's probably the original surface, and unchanging as the other moon.
So it's original factory settings.
Yeah. Well, pummeled by rocks.
Right. Wow.
As compared to, Ganymede, Europa, and Io, which resurfaces itself every day, right? Those still have some geologic activity going on, whereas Callisto doesn't really.
Wow.
Yeah. So you can see it. There's just so many craters you can see.
Yeah. Dang.
And this is what Callisto looks like. So this crater, I think, is called Asgard.
Ah, nice.
There's another one called Valhalla.
Nice.
Good naming scheme right there. So this is, so that crater is, I think it's this guy up here.
Okay.
Or is it down here? I can't remember.
It's the white one.
It's a white crater on Callisto. It's a big one. You won't miss it. So you can see other. So you can see this crater here. Again, it doesn't really look changed compared to the others, where it looked like it kind of might have filled back in a little. This one doesn't really have that. Now, I think on this mission, in the extended mission, they do discover evidence of landslides.
Oh.
Yeah. It's either this one or Ganymede, they have evidence of landslides. I had a picture of it, so.
Okay.
Yeah, so this is what Callisto looks like.
It's just craters.
Yeah, and I think these ridges, you can see they're kind of radiating out.
Yeah.
I think they're on the opposite side of an impact crater.
Oh, okay.
We actually found this on Mercury. There's a massive impact crater on one side of Mercury, and then there's ridges on the other side from where because it hits it, and it's going to shake and wiggle a little bit, so it opens up on the other side a little.
Oh, wow, okay.
Yeah, so I think that's what would have done that.
Huh.
Yeah, it's so fascinating.
Yeah.
And we're just seeing pictures, just doing a little flyby overhead versus, landing and looking on the surface. That's the other reason why when people complain about, we're going back to the moon, we've already been there. No, we haven't.
Yeah.
We've explored, right? It's as if the Apollo missions landed in our backyard and took samples and left, and that's about all we've really seen of the moon, right? But for Earth, right? Earth's big and dynamic. These moons are big and dynamic. Maybe not as big and dynamic as Earth, because Earth's got oceans and deserts, and we have life. But there's still so much that's going on.
Yeah. There's still so much.
And you can see mountain ridges.
Whoa.
Yeah.
Look at that.
Aren't they amazing?
That is incredible.
Yeah, as you can see, you can kind of guess how tall they are based on the images and kind of the pixel sizing. I didn't get any of the data for that, but they're big and interesting.
Yeah. Wow. You can see that the part of the land over to the right is much lower than the land to the left.
That might be the crater wall of this guy.
Oh.
Might be. Because you're doing a flyby, it's the same spot. You kind of edge on and look at it.
Right.
It might be that. Because you can see also here, look at you see the cratering here, right? It looks more like the moon than the others. Because there's no surface dynamism.
Yeah. So, it also looks very, very... I don't know. Well, I've lost a word for it, but it's very rough.
Yeah.
It's very imperfect.
Yeah. Because it hits it and it stays.
Yeah.
Where the others will... Io will just like, nope, you're not there. Go away. Bury it. Go
Yeah,
away.
it's just going to flood it over with
go away.
sulfur.
You like sulfur, son? Here's some more.
Here's some sulfur.
There you go. Or Europa, slowly just kind of massaging out to the tidal forces. But this doesn't really change.
Oh, just static.
It's... Yeah. You can see, again, there's more of the craters. So I think they've... Yeah, so if you look in these craters, right, it looks kind of dusty.
Mm-hmm.
So they think there's landslides that are going on. So there's still some tidal forces from Jupiter, but not as strong, so it might be causing some of this to happen.
So it just caused a little bit of that erosion, just a tiny bit of landsliding occasionally.
Yeah. It's so interesting. And then this, I think, is the impact crater that made the shape on the other side. So this, I think, is Valhalla.
Ah, okay.
Yeah, this is Valhalla crater. It's big.
That looks huge.
Yeah. And again, so you can see on this image here, right? There's a little crater with a mountain in here, but there's another one right next to it, right? Because there's the mountain, and then there's the
edge. Yeah.
It's so, and just look at it. There's just so much to see.
Yeah.
It's so cool.
Look at that.
And it's peppered. It looks kind of like ceiling, like popcorn ceiling.
Yeah.
That's what it looks.
Yeah. It definitely has that texture.
Yeah.
You can also see the lines kind of at 45-degree angles over on the left.
Yeah, like here?
Yeah.
Oh, yeah.
Yeah.
That's so cool.
Yeah.
Again, if you're a planetary geologist, seeing these pictures come in was just heaven.
Must have been.
Oh, yeah. It's so cool.
Finally getting up-close images. Like, imagine if we did send out a mission to, like, the moons of Uranus and Neptune, right? And we got images of those back.
Oh, Miranda would be so cool to see because right, that one looks like it just fell apart, was put back together. It's got such dynamic features. Or the cryovolcanism on Triton.
Yeah. Yeah.
It'd be so cool.
That would be awesome.
It's big. That's what makes solar system exploration worth it. Just even the imagery alone is just astounding. Yeah. We'll talk about this at the end when we do the conclusion to the mission, but
the protein made the trip worth it. Sorry, that's the only thing I could think of.
Oh right, Paul, right? No,
K-Pax.
K-Pax. That's what I was thinking. You ate the banana. Yeah, it was one of those two.
Yeah.
So we're talking about what also Galileo saw, because it's not just looking at the moons and taking pretty pictures. So Jupiter observed so Galileo saw Jupiter's rings, right? It's got rings. What's going on there? I mean, Saturn's got much more interesting rings, but Jupiter's got them too. It's actually got 3 rings. It's got the big one, that's the one everyone sees, and then it's got 2 smaller rings. They're called gossamer rings. And they're on top of each other. There's a diagram on the next page.
Oh, okay.
Yeah, they just kind of overlap. They're really thin on top of each other. So it's theorized that they're formed from dust impacting the 4 inner moons. So not the Galilean moons. There's 4 moons even closer to Jupiter than the Galileans.
Oh, okay.
But that's it for the inner moons. I mean, the rest are just way out there. So they think they're from, it's Amalthea, not Almathea, Amalthea, and Thebe's orbital characteristics are related to the rings, kind of like the moon, shepherd moons, kind of.
Oh, okay.
Kind of like, again, what we see when we do Cassini, we talk about Saturn for 8 hours. We'll talk about shepherd moons and how the dynamics of that ring system.
Okay. Because that'll be interesting.
Oh, that'll be so interesting. So many good pictures from Cassini.
Oh, yeah.
What also observed, Galileo, were auroras. These are auroras on Jupiter.
Oh, wow.
Yeah.
Look at that.
The interesting thing is they were lower than predicted in the atmosphere.
Really?
Yeah.
We expected to be really high up?
Yeah, I guess so. Again, I'm not a planetary geologist or atmospheric dynamics guy, so I can't say, well, actually, it's supposed to be at this altitude, these kilometers with this composition, but I don't know why. It's just they were lower than anticipated.
Okay.
It also looks at the atmosphere and the atmospheric dynamics. Just going to say that so we can kind of get there. It also got some pictures of the 4 inner moons, but it got better pictures later on after the primary mission.
Oh, okay.
So we'll get to that. So let's take a look at some of these pictures. So this is the rings, right? So that halo is the intense radiation belt that the probe discovered on the way in.
Oh.
Yeah. Of helium.
Okay.
So you have the 4 inner moons, right? You got Amalthea, Adrastea, Metis, and then this is Thebe. It got cut out. And you can see they got the main ring right there, right? So this is the main. I think this is the main ring. Yeah, and it's
Okay.
got thinner rings out here. They're called the gossamer rings because they're like gossamer, which is like I forgot what it's what's the what am I thinking of? Like really thin fabric, right?
Okay.
Like in the like old timey, like you know how old timey stuff they always had the little thing draped over tables and like those.
Yeah.
The really thin versions of that, they're called gossamer.
Oh, okay.
Yeah, so they're really thin rings, and they're made by interplanetary dust hitting these moons.
Wow.
Yeah, it's a lot
So
of
basically the crumbs of these moons' meals.
yeah, just exploding.
Nice.
So this is Jupiter's atmosphere. So this is thermally what's going on, right?
Okay.
So this is storm systems. You can see there's more hot in this storm, and there's not so hot, a bit more hot, right? You can see there's different bands to Jupiter's atmosphere from heat,
Mm-hmm.
chemistry, atmospheric storms, all that.
Mm-hmm.
This is what the red spot looks like. It's actually cold compared to the rest of
Oh.
Jupiter,
Yeah.
which is really interesting.
That is interesting.
And then, so this is Jupiter taken in infrared during an eclipse.
Ooh.
That's lightning. I think
Oh.
that's lightning, yeah. And this is just the atmosphere of, this is what Jupiter looks like.
Yeah. Like that's incredible though. Look at
Oh, yeah.
how beautiful
It's
it
just
is.
gorgeous. All of that going on. It's all larger than Earth. It's
Yeah, of
enormous.
course.
And it's clouds of ammonia. Ammonium's like hydrogen sulfide and some water. Methane. Just so much is going on.
Mixing, traveling at different speeds, rising, falling, warming up,
Storms.
cooling off. All just swirling together.
It's astounding. Again, the pictures from Juno, I think, are some of the best of Jupiter.
Yeah.
Oh, they're
Remember, this is with a potato camera
Yeah.
on a tape recorder
Yeah.
built in the 80s,
Yeah.
launched in the 90s.
Yeah. So this is the Great Red Spot, obviously. This is what it looks like, I think, this is also false color. We actually see a real color image of some storms later on.
Okay. Okay.
So this is what kind of, so this is actually a hot spot right here. And you can see there's, right, atmosphere is moving in here. It's curling around this. While this band is going this way in terms of atmospheric, flows.
Okay.
It's going the other way. It's this massive dynamic atmosphere, right? Giant Hadley cells, right? So much is going on.
It's all mixing together.
And we don't know anything about planetary science to appreciate this, which is very unfortunate if you ask me.
Yeah,
But-
it's pretty unfortunate.
So this is Jupiter with NIMS with different, spectra. You can see different hot spots, different cold spots, different storms, what's going on, right?
Mm-hmm.
You can see kind of, I think this one's kind of interesting. It's like an Andy Warhol painting. When I think about it,
Yeah.
right? You got the different, so that's what's going on.
I mean, I like how in each of them you can clearly see the Great Red Spot.
Yeah, it's a giant storm. It's been going for, 300 years, I think, and it's not letting up.
Yeah.
So
Yeah.
interesting. And you can kind of see, the different swooshes here from the...
Yeah, the turbulence from the storm.
Yeah, which, again, the size of planets.
Yeah. Because it's like, what, 10,000 kilometers across right now?
Yeah.
Or 10,000 miles across,
Well-
which is bigger than Earth.
When we get to the Millennium mission, I think, we're going to see two storms the size of Earth collide.
Oh, dang.
Yeah. And in this picture right here, so that
Uh-huh.
that is lightning.
Ooh.
That's lightning on Jupiter.
Wow.
It's got lightning,
It's got lightning.
which is really cool. And this marks the end of the primary mission and this
Oh.
episode. I thought we'd take longer to talk about the different imagery, but I guess not.
You didn't really have a whole lot to say besides from look how beautiful it is, and we don't know anything about planetary science.
Want to keep going?
Yeah, how long has it been?
50 minutes.
I think that was a good, pausing point.
Okay. So we'll cut that little dialogue out and play us on out.
Yeah. Just what does that mean? What does it mean? Play us out.